Good evening, students. So, as you know, we are studying about the P block element. In class 12, about the group 15, group 16, group 17, and group 18 elements, and its detail we have to study. In the last video, I have explained about the elements of the group 15, configuration of group 15, and variation of some physical property like electronegativity, ionization, enthalpy, size, etc. So one more important property, that is oxidation state. In this, as you know, group 15 element has the general electronic configuration. Group 15 elements have general electronic configuration Ns2 and Np3. It contains 3 electrons in the p subshell. That means 3 unpaired electrons are present in p subshell. So oxidation state can be explained by 2 methods: by losing, or you can say by the transfer of electron, and by the sharing of the electrons. As we know, there are 3 electrons in the p subshell, and it requires 3 electrons to complete noble gas configuration. The elements which are having high electronegativity and smaller in size, like nitrogen and phosphorus. They are smaller in size and have high electronegativity. They can show the formation of triple negative ion by the gaining of 3 electrons. They gain 3 electrons and complete their p subshell and form the noble gas configuration. In this way, nitrogen is converted into the N triple negative, while phosphorus into P triple negative. So student, what do you think the oxidation state of the group 15 element is -3? But as we move from downside, arsenic, antimony and bismuth, what we observe, they are larger in size and their electronegativities are very low. So they have very less tendency or no tendency to gain electron. So they are unable to achieve 3 electrons, and they are unable to show the -3 oxidation state. The common oxidation state of group 15 is -3, but this tendency to show the -3 oxidation state on moving from top to bottom decreases. Why it is decreases? Because nitrogen to bismuth size increases and electronegativity decreases. Due to the very less electronegativity, bismuth, antimony and arsenic, they are unable to show -3 oxidation state. That means by the gaining of electron, only 2 elements of group 15, nitrogen and phosphorus, can form triple negative ion. So this is the explanation on the basis of the transfer of electron. That means nitrogen and phosphorus can easily show -3 oxidation state. Now the other case, second case, by the formation of covalent bond or by the sharing of electron. As we know, the general electronic configuration of group 15 is Ns2 and Np3. So they can form 3 covalent bond like this. They can form 3 covalent bond or by sharing of electrons and achieve the stable configuration. In that case, the nitrogen and phosphorus easily form the 3 oxidation state. On moving from top to bottom, nitrogen to bismuth, what we observe, the size is larger and this NS2 electron behave like inert pair. Due to the inert pair, they are unable to show the 5 covalent bond. Nitrogen has 3 unpaired electron, while phosphorus also has the 3 unpaired electron. In the phosphorus, what we observe, D subshell is also present. Nitrogen is not having the D subshell because it contains only 2 shells. In the second shell, there is unavailability of D subshell. Phosphorus containing 3 shells, so it has D subshell also. So phosphorus can also show the 5 oxidation state. That's mean when this electron move from here to here, so it will form in the first oxidation state 5 oxidation state like this. So on moving from top to bottom, tendency to show +3 oxidation state and +5 oxidation state increases. Means when we go from nitrogen to bismuth, they can show -3 to +3 oxidation state, or they can show +5 oxidation state. But dear student, due to this inert pair effect, no element will show or the +5 oxidation state below sides. So what do you want to understand here? I want to tell the common oxidation state of group 15 is -3. But on moving from top to bottom, tendency to show -3 oxidation state decreases. Why it is decreases? Because the size increases and electronegativity decreases. Second thing, they can show +3 oxidation state, and on moving from top to bottom, it will increase. And +5 oxidation state is not possible because of inert pair effect. Okay, students? Phosphorus can show +3 and +5 both the oxidation state. See, in the compound PCl3, the oxidation state of phosphorus is +3, while in PCl5, oxidation state of phosphorus is +5. Nitrogen do not show +5 oxidation state in the form of halide. Nitrogen can form only the NCl3, not NCl5, because D subshell is not present in the nitrogen. But dear student, nitrogen can show all the oxidation state -3 to +5, but in different compound. See the compounds in which the nitrogen show these all the oxidation state. If we see the ammonia and H3, the oxidation state of nitrogen in ammonia is -3, and the oxidation state in hydrazine NH2, this is -2. How you will calculate the oxidation state of nitrogen in hydrazine? Here we will take X for nitrogen, 1 into 2 plus X plus 1 into 2, that's equal to 0. So 2X plus 4 is equals to 0. So 2X is equals to -4. So X is equals to -2. Now see, in hydroxylamine NH2OH, oxidation state of nitrogen is -1. Then nitrogen in N2 molecule, oxidation state will be 0. And in N2O, nitrous oxide, so oxidation state will be +1. Please check how it will be the +1. 2 into X -2 is equals to 0. So 2X is equals to 2. So X is equals to 1. While in NO, nitric oxide, oxidation state will be +2. Then in HNO2, oxidation state will be +3. And in NO2, nitrogen dioxide, oxidation state will be plus 4. And finally in HNO3, oxidation state is plus 5. Means nitrogen can show all the oxidation state which are possible in the group 15 according to this, but they are not shown plus 5 oxidation state in the form of halide. Okay students, now moving towards the chemical reactivity or chemical properties of the group 15 elements. The first one, formation of the hydride. Formation of hydride. All the elements of the group 15 form the hydride, and the formula of the hydride formed is MH3, where M is the element of group 15. The first member of nitrogen and it formed NH3. It is ammonia, AMMONIA, while PH3 phosphorus form hydride, that is called phosphine, PHOS PHINE. Then arsenic form ASH3, this is arsine. Then antimony form SbH3, stibine. And bismuth form BiH3, bismuthine. So if we will see the structures of these hydride, so what we observe, they all contain 3 covalent bonds and 1 lone pair. The structure having like this. This is group 15 element and form a pyramidal shape. This H, H, H. It contains a lone pair electron, where we can take nitrogen, phosphorus, arsenic, antimony in place of M. This shape is called pyramidal in shape. As we are seeing the bond angle between the hydrogen and group 15 element, as you can say HMH bond angles. In case of ammonia, phosphine, arsine, stibine and bismuthine, what we observe on moving from top to bottom, that means from ammonia to bismuthine, the bond angle HMH will decreases. Why it happen? As we go downside, size of the central atom increases. Nitrogen is the smallest atom, while the phosphorus is little bit bigger. And on moving from bottom side, bismuthine is the biggest one. As the size of the atom increases, electronegativity decreases, and the tendency of electron to attract towards itself decreases. That's why the density of electron at the central atom present here will be decreases. Nitrogen is the smallest one and it has the highest electronegativity in group 15. So electron density in case of the ammonia will be maximum at the nitrogen. So when the electron density nearby the central atom in any hydride will be highest, the repulsion force between the lone pair and bond pair will be maximum. As moving downside, size decreases. When the size decreases, then the electron density also decreases. So the repulsion between the lone pair and bond pair will decreases and the bond angle will decreases. In case of ammonia, the bond angle, that means HNH bond angle is 107.8 degree. While going downside from ammonia to bismuthine, the bond angle decreases. So order of the bond angle on moving top to bottom will be like this. That means NH3 greater than PH3 is greater than ASH3 is greater than SBH3 is greater than BiH3. Okay, student. Now moving towards the other properties of the hydride. As we know that these compounds form NH3, PH3, ASH3, SBH3 and BiH3, which will be the most stable. So the point is thermal stability. Thermal stability of hydride of group 15. Hydride of group 15. NH3, N is the smallest in size, and the bond between N and H will be very strong and shorter. That's why NH3 required more energy to dissociate. So thermal stability of ammonia in all the hydrides will be maximum. The order of the thermal stability will be as follows. NH3 is greater than PH3 is greater than ASH3 is greater than SBH3 is greater than BiH3. Means ammonia required more energy to decompose, while bismuthine required very less energy. Now see the reducing agent. Reducing agent. Reducing agent. As you have studied here just now, the thermal stability of ammonia is maximum. That means it requires maximum energy to break the nitrogen-hydrogen bond. That means it is not easy to take hydrogen from ammonia. These all are containing hydrogen, no doubt, but the hydrogen from bismuthine will be easier to remove. That means BiH3 is the strongest reducing agent. So dear student, what will be the order of the reducing agent? We can say BiH3 greater than SBH3 is greater than ASH3 is greater than PH3 is greater than NH3. But dear student, we take ammonia as a reducing agent. No doubt ammonia is a good reducing agent, but these are also better reducing agent than ammonia. Now the next property, basic in nature. As we know, all the hydrides are group 15 hydrides containing a lone pair of electron. Basic nature. Basic nature. Group 15 elements like ammonia and H and H containing a lone pair of electrons. Similarly, phosphine also contain a lone pair of electron. That means they are Lewis base because it can donate one pair of electron easily. But on moving from downside, the basic nature decreases. Ammonia is strongest base of group 15 hydride. That means basic nature decreases. But arsine, bismuthine and stibine containing a lone pair of electron but has less tendency to give lone pair or to donate lone pair because of inert pair effect. So they do not show basic in nature. Ammonia is a stronger base than phosphine, and arsine, bismuthine and stibine are not basic in nature. Now the next property, formation of the hydrogen bonding. Formation of hydrogen bond. Ammonia containing nitrogen, and nitrogen is the most electronegative element, and it contains N single bond, H bond. That's why ammonia can form a hydrogen bond, because the size of the nitrogen is very small, as well as it has high electronegativity. One ammonia molecule can form 4 hydrogen bonds like this. Okay, students, getting my point? So, in this way, we can say formation of, but phosphine or cyne do not form hydrogen bond because the size of the phosphorus is larger and electronegativity of phosphorus is also less. Now moving towards the boiling points. Boiling points. Dear student, as you know, on moving from top to bottom, molecular mass increases, size increases, so boiling point should be increased. But in case of ammonia, due to the formation of hydrogen bond, ammonia has extraordinary high boiling point. So boiling point of ammonia is higher than phosphine, but according to the concept, it should be smaller. But when we will tell why ammonia has higher boiling point than phosphine, so answer will be because nitrogen is smaller and having high electronegativity, and it can form the hydrogen bond. That's why ammonia has higher boiling point than phosphine. If we go downside from arsine to ASH3, then SbH3, and then BiH3, so boiling point will increase successively. That means out of these three, arsine has a smaller boiling point than stibine, and stibine has lesser boiling point than bismuthine. Okay, students. Now moving towards the halides of the group 15. Halides of group 15. Group 15 elements can form two types of halide in the form of MX3 and MX5. MX3 means trihalide, while MX5 means pentahalide, where M is the group 15 element like nitrogen, phosphorus, arsenic, etc. Nitrogen is the first element and it cannot form pentahalide. It can form only the trihalide like NCl3, NF3 and Br3. And dear student, I want to inform one more important thing, that the existence of Ni3 is not possible. That means trihalide of iodine, trihalide of nitrogen is not possible. Why it is not possible? Because of a smaller size of nitrogen, 3 larger atoms of iodine cannot be accommodated in it. Nitrogen cannot form pentahalide. That means you will never see NCl5, NF5, because the unavailability of the D subshell, so nitrogen cannot expand its octet role. The trihalides of nitrogen NCl3 and F3 and Br3 are exist. But dear student, all other elements form trihalide as well as pentahalide. Bismuthine trifluoride also not exist. Bismuthine trifluoride and bismuthine pentafluoride is not exist. And dear student, phosphorus can easily form both the type of halide PCl3 and PCl5. This is phosphorus trichloride and this is phosphorus pentachloride. So phosphorus trichloride is more stable than phosphorus pentachloride, but phosphorus pentachloride is most important pentahalide of the group 15 elements. All the trihalides, that mean MX3, has pyramidal shape like this. It contains one lone pair of electron and it has sp3 hybridization, while pentahalides have trigonal bipyramidal shape, and the shape of the PCl5 will be PCl, Cl and this Cl5. In PCl5 the hybridization is sp3d. You are seeing there are the 5 covalent bonds in the PCl5. These 5 covalent bonds are not equal because 2 bonds are at the equatorial position and 3 bonds at the plane. So dear student, what we have studied today, the hydride of the group 15 as well as halides of the group 15. Now in the next video we will discuss about the new coming topic of the group 15. Okay, goodbye.